Okay, wish me luck. All right, so we did attendance, we did a little bit of recap. The first question I have for you today, and actually today I'm going to be a little bit generous and I'm going to pay you for your responses. So I didn't do this last class. I usually do it first class to break the ice a little bit, but first class is so boring. There's not a whole lot of questions that get asked or answered, so we'll start it today. If you ask a question or answer a question or make a correction or in any way are active in class today, I'm going to reward you by being pegged with a piece of candy, but my aim is awful. So if you are sitting next to someone who answers, asks, or catches a problem, duck. Or be ready to catch, okay? So usually it ends up with me embarrassing myself, which is good for y'all. So we'll do that today. So my first question for you today is, what is a model? What the heck is a model? Yeah?
It's a mathematical representation of a real system.
Okay, you jumped straight to mathematical, and that's true. It could be a mathematical representation. Specifically in our field in engineering, it most often is a mathematical representation. Yep, something to add, David?
So a way to predict the system's future behavior.
A way to predict the system's future behavior? Absolutely. Those are, I'm actually really impressed. Oh, I forgot to tell you, Candy. Oh, this is going to be interesting. I told you it was bad. No. Woo. Oh. Okay. Very, very good. You actually got more specific than I thought you would on a first try. So in general, it doesn't have to be a mathematical model. You could, build a thing in clay, which is the way you learn what a model is in like kindergarten. You learn that it's some representation of something else. It's not always perfect, right? Our clay has little bumps and grooves where maybe the real thing doesn't have bumps and grooves, or like our clay dog doesn't have fur, but a real dog has fur. Very similarly for us, when we build a mathematical model, we make certain assumptions about the system, and sometimes those assumptions are good, and but sometimes they're not so good, and they cause error between our model and our true system. And so what we've seen before is that most of the time the equations that we use to describe how a system is going to behave, like David said, in future time steps, is through a differential equation. So most often for us, it's a differential equation. And specifically in this class, someone asked last class about what makes this class simpler and later classes maybe more fun or allow you to control more cool things. And here's where it is. We are going to kind of zoom in, for the most part, on linear, time-invariant systems. You might say, wait, what do you mean by time invariant, right? A differential equation is specifically about something that changes over time. So how is it time invariant? Well, I'm not actually talking about the variables of the equation. I'm talking about the parameters of the equation. So over time, the mass of our block never changes. The spring constant of our spring never changes, or the dampening coefficient never changes. Those are time invariant. The parameters of the system don't change. This is different than, say, like a rocket ship. A rocket ship, when it is sitting on the tarmac, it's sitting on that launch pad, has a ton of fuel in it. And that fuel is a ton of mass. It makes up a huge portion of the mass of that rocket. And what happens as that rocket starts moving?
It's lighter.
It gets lighter, right? Because it's burning off that fuel. Okay, so with a rocket, we can't even do rocket ships in this class because we don't know how to deal with that mass changing over time. Okay, so yes, these are simplifications, but we always start with a very simplified system, and then through later classes we work up to complex, nonlinear, ickier stuff. Okay, so what I'm going to write down is a couple of notes here. A model, specifically for this class, is usually a differential equation. Now we did talk last class about these block diagrams. And I want to say that is a different kind of model, but in actuality they're really equivalent. It's really just a visual way of representing these same equations. So it's the same math behind it. It's just a visual representation of the inputs and outputs. So we will look a little bit at block diagrams, but I still want you to think about those block diagrams as being differential equations. just in the form of a picture. Okay, and then I said for this class, we will deal mostly, and I say this, but actually the very next class we're going to talk about nonlinearities a little bit, but for the most part, we are mostly going to deal with linear, time invariant, differential equations. And in the field, we will usually refer to these as LTI systems. LTI means linear, time invariant. Okay, so we're all comfortable, or should be comfortable, with recognizing that we can describe this system as a differential equation in the time domain. That's what we're used to. But there's something that's not so great about the time domain, and it relates to our desire to draw these things in terms of a block diagram. So for a plain Jane differential equation, I'm shortening DE as differential equation because I'm lazy. The input, output, and system parameters are spread all throughout the equation. But really, we would like for all of these things to be separate. We would like to represent our system where each of these things are separate blocks or signals. Okay, so also last class, I talked about, I believe I drew a very simple block diagram. I said, with a block diagram, we like to represent our system as having some input, and we called this our reference, and some output, which is some controlled variable. And in the middle, we have something that represents our system. Okay, so this is a very, very simple block diagram, but the way that our differential equation is written here, we can't really get it into this form. So for this system, remind me again, what was our input for this system?
Force.
Yep, we said as an engineer, I am allowed to decide what is the force on this block. And what was the output?
Position.
Position, which is X. Right, heads up, Angela. Well, sorry, Conrad. Please still come to group meeting later. Okay, so this is all well and true. This is great. But this is also a simplification. So it is also possible that our system is something really complex. Our system is so complex that it's actually made up of a bunch of subsystems. And these block diagrams can still handle this. We might say the signals that I really care about are over here at the beginning and the end, and those are still the input, R of t, and the output, C of t, but there's actually several subsystems in between. And that's well and good. We can still use block diagrams for systems like this, so I'll call this a subsystem. This is a subsystem. This is a subsystem. Okay, so let's think of a simple system where we can kind of make these ideas a little bit more concrete. So in the book and in the past and probably in every controls class ever, a lot of people like to think about an elevator as a very simple in some ways control system. So all the inner workings of the elevator, let's put that aside for now. Let's think with an elevator, and I'll draw a quick picture for us. I apologize, I'm not an artist. If you can't at all tell, yes, I use a lot of squares. If you can't at all tell what it is, I apologize. That's why I put these nice little labels. Okay, so I'm drawing an elevator. Elevator is a square on a cable, and that cable can pull it up or down. What is our input to our elevator system? How do we tell it what we want to do? You push the button, right? Okay, so our input here is our button push. But really, the information there is we're inputting the desired floor, okay? And in fact, I'm going to make it even a little bit more specific and say that's our desired position. We say, okay, elevator, this is where I want to be. And what is our output? It could be tension in the rope. We could look at it that way. But if you're just, so maybe an engineer might care what is the tension in the rope. But as a rider, do you care what the tension in the rope is? No, what do you care about? That you are actually arriving at the position you told it to go to. So for our output here, we're going to say this is the actual elevator position. Okay, and these two things are not exactly the same. Right, I tell it immediately, instantaneously. The second I hit that button, it says desired position jumps from wherever I am to this brand new floor. It's a discontinuous signal. But the elevator cannot transport from one spot to the other instantaneously. So the actual response of the elevator is not that perfect square wave. It's something that looks a little different. So let's fill out this picture a little bit more. So you told me that we care about the position of the elevator. That's our output. And just for making this easy, we sometimes refer to our position in terms of the floors that we're on. So maybe this is floor 0, floor 1, floor 2, floor 3. Okay? And I said, ignore my later drawing, I said that our input is this square wave. So if we look at what my desired input is, or my desired floor position, and I look at that signal over time, maybe I have some function of time, it would look something like this. Got to switch colors here. All right, before I got onto the elevator, my desired floor, we're going to assume that we're starting out at floor 0. Desired floor is just 0, where it's at, because I haven't told it otherwise. At time 0, which is the instant that I push the button, my desired floor jumps up to whatever floor I push. But for this thought example or thought experiment, we'll say this is just floor 1. Okay? So instantaneous jump. It is a non-continuous function. We actually have a special name for this function. Yeah? Jerry, we call it a step function. I'm not sure if you heard Jerry, but I'm pelting people with candy today. Well done. Not as fun for you because I actually got it to you. Okay, we call this a step function. This is going to be a very important function throughout the rest of this class. And in fact, it's so important that it has its own letter. We call this function u of t. It is a piecewise function that is 1 for t greater than 0, and it is 0 for t less than 0. Okay? So this type of input makes sense for our elevator system. But in other systems, like I said, we're going to look at a ton of different systems this semester. In other systems, our input might look a little bit different. It might not be a jump from 0 to 1. So in your book, there's actually all of these other input functions that we're going to look at and analyze our system response to. So we have another very special function here. What do we call this one? I heard it, R? Ramp function. Who am I pelting? Thank you, Amari. Sorry. Thanks for the assist, Amir. Yeah. I gotta make sure I sound nervous when I do it to make you extra anxious. Okay, so here we have a ramp function. How is the ramp function related to the step function?
Like the derivative of it, or it's the other way around.
It's the other way. What's the inverse? Yep. Integral. Yeah, you said it. Whoop, and I sucked again. Okay. So as a quick aside, the ramp function is the integral of the step function, and in fact, we look at a couple of different further integrals from there on. So in your book, you have a nice little table that describes these interesting functions. So I started here at the step, which is this nice discontinuous, but continuous thereafter. Above that, the derivative of that one is actually the impulse, where you have an instantaneous value that's really high, but it's only that value at t equals 0. If we were thinking of this as a force, it might be something like you hit your robot with a hammer really quickly. So you have a very, very fast force. It's there and then it's not, almost instantaneously. We model that as an impulse function. And that function we give a delta. So we have delta as impulse, u is step, ramp is t times u of t. We can take another integral and get parabola. And then other times we're going to talk about forcing functions that are sinusoidal. So either sine or cosine or some other sinusoidal function, okay? With our sines, we can play around with the amplitude of our forcing function, and we can play with the frequency of our function. So frequency, and then if we add a constant out here, we're playing with the amplitude. Okay, so just as an aside, to give you a heads up that this is not the only input function that we'll be working with in this class. But it makes sense for our elevator. Okay, enough about inputs. Let's talk about outputs. All right, so I said our output is not the same as this nice square input function. Our output has to obey the laws of physics, which says that elevators don't apparate and disapparate all over the place, if you're a Harry Potter nerd like me. In fact, they do a slower rise, and they will maybe slow down as they approach the goal position. Okay, so the blue line here is desired. Red line here is what actually happens, so we'll say actual behavior. Actual behavior. Okay, so if we were to think of this in terms of a block diagram, we might represent our input here as this step function u. So our reference is this u function. We have all of the system in here, right? That's like whatever it is inside of the elevator that takes that button push, which is probably an electrical signal, turns it into current added to a motor that causes the motor to spin, which causes torque, which probably winds up a cable, which creates tension on the cable, and finally, which creates motion of the whole thing, which is the thing that we care about. And really, we care about these two things. And we would kind of like to abstract away what's in the middle here, okay? So we represent that as our system, our elevator system, and all those intermediate steps, those are all subsystems. The one that went from button push to whatever I said. Button push to motor to tension, or to torque and then to tension, okay? Now, block diagrams, it's important to know, if you are assessing a block diagram, you are multiplying your input times your system to get your output, okay? So let's dive into what that means a little bit. I'm going to say block diagrams multiply. And I know that's a little vague, so here's what I want you to think about. I want you to think about the way that we abstracted what's in that elevator system box as being this ratio of output over input. Such that the way we would interpret this block diagram is that R of t, which is our input, times, I'm going to write it in words. Input times output over input equals, what happens? They cancel, right? We get output. Okay? So the question is, we're still left with this issue of time domain equation of motion does not do this thing where we can organize it quite this way. but we want to think about it that way. So enter stage left, if we're speaking theater here, the Laplace transform. The Laplace transform is the math that lets us go from time domain to frequency domain. And in the frequency domain, we are very easily able to find this transfer function thing. Oh, sorry, this is transfer function. Okay, so here we go, enter stage left, Laplace transform. So we'll say Laplace transform. What is this thing? This thing is a linear operator that maps a time domain function into a frequency domain function. I want to take another quick aside because I think this is important background information that you may or may not have gotten in previous classes. I specifically said that this thing is a linear operator. That says something really important in mathematical terms. Can anyone tell me roughly what is like the behavior you can expect from a linear operator? What properties do you get? Not quite what I'm looking for. Straight line, still not quite what I'm looking for in terms of an operator. Hooke's law is a linear function. Hold on, I need to distribute candy. I never make it to that first row. I second guess. Matthew, did you answer? Yeah. Who else?
No, I didn't answer. I was going to answer.
Sorry, I got happy. Let's go into the math of it. Well, I'll talk about it. So a linear operator refers to a function that preserves vector addition and scalar multiplication. Okay, so what this means is that if I have my time domain function and I multiply it by some scalar a, what can I expect to happen for my Laplace function in terms of s? Also multiplied by a. So scalar multiplication, if you do it to one, you get the same thing in the other. Okay? Now, let's say I have f of t is actually an addition of two other time functions. So we'll say f of t, you can split it up into some g function of time and some h function of time. It turns out that if I take the Laplace transform, this is a sneak peek, that's the operator, that's the symbol we'll use to represent the Laplace transform. It's just a cursive L, in case my cursive is too horrendous for you. If I take the Laplace transform of f of t, where f of t is actually the sum of these other time functions, what do you think happens?
Same thing, just uppercase, still adding them together.
Well, so we definitely suspect that we can do this, but what is not obvious, what it takes a linear operator to do, is that we can kind of distribute that operation to each of them in turn. So it's really Laplace of g of t plus Laplace of h of t. Those are still equivalent for a linear operator. Okay? So just a couple of tricks that we're going to need for some of the math we'll do in a moment. Okay, so I said there's this Laplace transform thing. I gave you a symbol for it, and I told you some properties. What is it actually? It is actually something that looks really gross, and if it makes your stomach hurt or it makes you want to leave the class, don't, because we don't actually end up using this form of it almost ever. But we will today, okay? So here's the real, actual definition of the Laplace transform. The Laplace transform of some f of t, some function of time, we will represent as the uppercase of that same function. So whatever variable we use for the function, we just make it uppercase to denote that it has been Laplace transformed. We say that this is the integral from 0 minus, which is the weirdest part of this, to infinity of f of t times e to the minus st dt. Okay? And then we will add here where s is this sigma plus j omega, which is a representation of a complex variable. Quick review, what's a complex variable?
Has I in it.
It has I in it. Okay, I just wrote down a bunch of letters. Are any of those letters I? J is the same as I. Brilliant. That's very good. So both J and I equal the square root of -1, which is the imaginary number. Okay, we're going to work a lot with imaginary or complex numbers in this class. Yep.
What is the 0 and then the negative?
Let me get to that in just a second. I will get there. Candy? Conrad, you're getting like bullseye today.
Get one every time you hit them.
Oh, that's probably true. I'll bring it whatever's left to group meeting. So, fun fact, and I learned this from Dr. Hubicki's lectures, is what do electrical engineers tend to deal with? What is their deal? They deal with electricity. Yeah, they deal with electricity. So they really like the equation V equals IR, right? What is that I? Current, right? They use I. Everyone else tends to use J. Unless you're an engineer, we kind of all decided like, okay, let's do I. But sometimes mathematicians will also use J. So either one is correct. It's the imaginary number. Okay. Let's see. So a complex variable is not just the imaginary part. A complex variable has what? A real part, right? So this is the real part. We'll call this real. And this is the imaginary part, the part that multiplies with I or J. All right, just wanted to do a quick aside on complex variables. Okay, just to be formal here, we call f, sorry, that's not very clear that that's capital. We call f of s the Laplace transform of f of t, lowercase f of t. Okay, if we can Laplace transform it, do you think we can go back the other way? Yep, we can. What do you think we call it? The inverse Laplace, some of y'all read, good job. Inverse Laplace transform. I denote that with just a -1 in the exponent of the operator. So the Laplace transform, or the inverse Laplace transform, is again this really icky thing, so don't stress out too much. We don't use it all that much, but we will today. 2 pi j integral sigma minus j infinity sigma plus j infinity f of s e to the st ds.
Dr. Higgins, can you move it up a bit?
Yes, ma'am.
Thank you.
Oh, you said something. Congrats.
Add to your pile.
If you got something you don't want, feel free to trade out at the end of class.
No, she created a little pile here. So.
Nice. Okay. So this is equal to, this isn't actually equal to f of t. It's actually equal to, if we're being very precise about it, it's actually equal to f of t u of t. And this is where we need to try to make sense of that little 0 minus. So Remind you that u of t is the step function, which is equal to 1 when t is greater than 0, and 0 when t is less than 0. And this is the step function. Okay, so what do you think happens when I multiply this step function times any other function? What do we get out?
Put up the function.
Okay, what happens when t is less than 0?
Zero.
It's always 0, no matter what you multiply it by, it's always 0. What happens when it's after 0? It's just whatever you multiplied it by, right? Okay, so why do we have to say that we don't know what's happening to the left of 0? Well, yeah?
Isn't it like a continuity issue? Like, don't you have to be like just before 0 so that you don't have, like a, oh god, what's the term? When you like jump up and it's non-continuous or something like that?
Okay, you're on the right track, yeah. You're gonna get diabetes if you keep answering questions. Yes, so it has to do with that, but so that gets to the 0 minus issue. So if the Laplace transform does the integral only from, so that little minus means just to the left of, like an infinitesimal little bit, just to the left of 0. If there were a plus on it, it would mean just to the right, or infinitesimally to the right of 0. Right, we talk about this sometimes in Calc 2 when we're talking about limits that exist or don't exist. We evaluate the function from the left and we evaluate the function from the right, and if they're not the same, they're discontinuous. Okay, if we start just to the left of 0 for this integral, when we go back the other way, we can't just make up information about what happened before that point. Right? Our integral started at just before 0, so we only really understand what happens to this system after 0. Even if we inverse Laplace transform, we miss that information going back the other way. Okay? Now, why is it important that that integral starts from 0, or just to the left of 0? Is because of this discontinuity thing. And it turns out that the Laplace transform handles a discontinuity at 0 perfectly fine, as long as the integral converges. So as long as you can do the integral across some non-continuous something happening at 0, the Laplace transform is fine with it. Okay, so why does that matter? Let's go back to some of the inputs we said we were going to be dealing with. Are all of these inputs continuous before and after 0? No, they're definitely not, right? They instantaneously jump like specifically at 0 to something and back to not 0. So all of these inputs are highly discontinuous at 0. And the Laplace transform says that's okay. Okay? But we still don't get negative time. But also, what even is negative time? Right? Well, maybe. Yep, Jerry.
Wouldn't the parabola and sinusoid be continuous at 0?
It can be. It can be. Yeah. It's not that all of these are completely discontinuous, but yep. Okay. All right. Let's do, we talked about that. I'm not going to write it down. Let's do an example. So this is going to be the very first time you take a Laplace transform, and we're going to do it in a way that you will probably never do again, just so you know. Let's do example 1. Example 1. It's kind of like when you first learned derivatives. Do you remember when you first learned derivatives and they made you use the long form, like it was f of x minus f of x plus dx over dh, something like that, and they made you do it that way for like a week, and then they taught you, well, actually, you just bring down the exponent, and it made you really mad? I'm going to do that to you too, but we're not going to take a week to do it. I'm just going to do one example. Okay, so we're going to find the Laplace transform. Find the Laplace transform of our function of time, which is some scalar a e to the minus little a t times our step function u of t. All right, so let's remind ourselves of the definition. of our Laplace transform. I'll provide it for you. So remember that our big F of S is equal to the integral from 0 minus to infinity of f of t e to the minus st dt. And so this is just the definition of the Laplace transform. I haven't substituted in our actual f of t yet. Okay, so let's do that. Let's substitute in. Okay, we have an integral from 0 minus to infinity of, what is our f of t? Well, it's a e to the minus at u of t, all times that e to the minus st dt. Oh, I have an extra here. There we go. Okay, so here we're going to use our. So let's think. What is the only thing that could potentially be discontinuous in here? Is e to the minus t, is that discontinuous? Right, the u of t. So we need to think a little bit about the u of t. The u of t is what for anything to the left of 0? So anything to the left of 0 is not going to add anything to this integral, okay? Because it's u of t. So in actuality, we don't need to worry about the minus so much, okay? So because u of t is the discontinuous part of this, we can say u of t equals 0 for all t less than 0. Equals 1 for t greater than 0. Okay, so if it's 1 for all of the time steps that we care about in this integral, do I really need to care about it? It just goes to 1, okay? All right, so what I'm left with is really just the integral from 0 to infinity of a e to the minus at e to the minus st dt. Okay, when two terms multiply that have exponents, what do you do with the exponents? You add them, right? And these have these weird negatives, so I'm going to take out the negative. I'm going to factor out the t, and we just have a plus s or s plus a. They're both negative. I'm going to add in my equals here. Okay, just going to give us a little reminder, little hint again. The integral of e to the x dx is just what? It's e to the x, right? And then e to minus infinity. Let's think of maybe what that graph looks like for e. It starts way out here, goes up here, and it crosses 0, 1. So what is e to the minus infinity? 0. It approaches 0. And what is e to the 0? 1. Anything to the 0 is 1. But you can see that if you plug in 0, you get 1. Okay, we're going to need that in a second. So let's go ahead and chug through this integral. So you could do u substitution here. So if you're integrating e to the just plain x, it's just e to the x. But because it's not just plain t right there, we have to divide by the extra stuff in that integral. You could work through it and do u substitution like you did in Calc 2. You can convince yourself afterwards that you can just divide by the extra of that exponent. So what we end up with here is a e to the minus a plus s of t, but we can't forget to divide by the extra, which is minus a plus s. And then we need to evaluate that at our limits of the integration from 0 to infinity. Okay, so if I plug in infinity for t in the top, what do I get? Just e to the minus infinity. Yes, ma'am?
Sorry to go back so far, but,
No problem.
you said when t is greater than 0,
Yes.
when is it equal to step from?
Yes. Yep, definition of the step function. Someone's gonna have to, I don't know that I can get this back there. Jerry, toss it back to her. Oh, I got close. Okay, great. All right, so e to the minus infinity? 0. Okay, so when I plug in infinity here, this term goes to 0, which causes everything to go to 0. So I have 0 minus, let's plug in 0. What is e to the 0? 1. So I should be left with a times 1 over minus a plus s. Okay, this all simplifies down to, if I get rid of the ugly 0 and I do my negatives, I get big A over s plus a. Okay, so this is equal to, don't forget, this is the Laplace transform of f of t. So do you see any more t's? T's are gone. S's are in. S's are hot right now. S is the new t. Okay. Was it fun to do that integral? Oh, okay. Well, you're better at math than me, apparently. I don't particularly like doing the integrals. So what ends up happening is, instead of doing these integrals over and over and over and over again, we have nice Laplace transform tables that tell us what the Laplace transform is of common functions that we might need to do the Laplace transform of. Okay? Things like the impulse function, the step function, the ramp function, the parabolic function, e to the at times a step function, and our sinusoids. Okay? We can just read these off of a table. So in fact, let's look and see if we can compare what we tried to find the Laplace transform of and compare it to our table. So we have some constant a, e to the minus at times the step function. Okay, so we had minus a, e to the minus at times u of t. Okay, well, let's see. Do we have that on our table somewhere? Yes. Which one? Number 5. Pick number 5, my lord. Yes, it should be. And what happens to our a? It just gets pulled in because it's a linear operator. I'm done giving you candy. So we should have a times a divided by s plus a. Is that what we got? Ah, we did it. Woohoo! We don't have to do that integral ever again. It's on the table. Okay? Let's just chug through, for the sake of completeness, going back the other way. Okay? Let's do an inverse Laplace transform. Okay, so let's find the inverse Laplace transform of a e to the minus at. Oh, wait, no. Oh, I'm way ahead on my notes. That's why. Let's go down here. Find the inverse Laplace transform of f of s equals 1 over s plus 3 squared. Okay. We are actually going to use our tables for this one. So let's look back at our tables and see if we can find some things that look like 1 over s plus 3 squared. So we're looking for something that looks like there. Which theorems do you think might be useful here? 3, yeah, okay. So we have something that's 1 over s squared, but there's this weird, like, instead of it being an s, it's like an s plus a something. 5 as well. Whoops. Yes, so I think that it's actually one down here that is very similar. Okay, that tells us that we can change out s for an s plus a variable. Okay, so one way to think about this is, if we were to compare this function to this theorem, this says that we have an s plus an a somewhere in the Laplace transform. What number do you think our a is for this function? 3. A equals 3, right? Okay, so a equals 3. Okay, so we know that if we were to have some function g of t that was just e to the minus 3t f of t. What do you think our f of t is? Shane? Right. We need to refer back to here. Okay. So we'll have, let me actually take, trying to figure out how I want to explain this because it's kind of like a nested function. Okay. So we'll say, if we have something of the form g of t equals e to the minus 3t f of t, then big G of s would be f of s plus 3. So let's compare this to what we actually have. We have something that is not just f of s plus 3. It looks more like 1 over s squared, right? So that means that this function here is our big F of s plus 3 is 1 over s plus 3 squared. So our F up here must be whatever this inverse is. So t u of t. Okay, so let's plug that in and see what it looks like. Let's say f of t equals e to the minus 3t times u of t. Okay. That was a little challenging because it was kind of nested within itself. For the most part, we're not going to deal too much with these nested functions. We're actually going to deal with a lot of terms that look like, for the most part, we'll look at terms that look a lot like this. And we're about to do an example of one that looks like that, okay? Okay. So as a mechanical engineer myself, I tend to lean toward, yeah, Angela?
Go back up just for like 2 more seconds.
Yep, sorry. Sorry, I get a little scroll happy sometimes. I like to deal with mass spring damper systems. It's the mechanical engineer in me. But remember, we're just talking about differential equations. So what comes next? It could be a mass spring damper system, or it could be a circuit where you've done Kirchhoff's laws and you've summed at nodes and branches and whatever it is you do in electronics. Yes?
Could I see the frequency shift here?
Yep. These are both in your notes, both of these tables, and I will erase all of my nasty things here, and I'll post these notes to the Canvas, so you'll always have these tables. It wouldn't be a bad idea to print off these tables and just have them every time you do homework, because we are going to continue using Laplace transform tables all the time. All right, we good? All right, sweet. Okay, so because I like mass spring dampers, we're going to start with a mass spring damper. So let's assume some system parameters here. So let's just assume what the mass, what the damping coefficient, the spring constant, and F are. Let's say we have a mass equal to 1. I'm not even going to care about units. Let's just play with numbers today. K equals 3. And we'll say I'm going to force it with 9 u of t, which means that I start out with 0 force. At time equals 0, I give it 9. Instead of 1, I get 9. Okay, so let's take the Laplace transform. Take Laplace transform. So if I take the Laplace transform, I will want to take the Laplace transform of, m is 1, right, that's why. X double dot equals Laplace transform of the left equals Laplace transform of the right minus 4 x dot minus 3x plus 9 u of t. Okay, so we're gonna need to go back to our tables because we haven't yet looked at the Laplace transform of a differential equation. So we have this x, which is a second derivative of x. Let's go back to our tables and figure out what the Laplace transform is there. So it's in this later transform theorem table where the Laplace transform of, let's first look at the first derivative. If we do the first derivative, we take an s and we multiply it times the Laplace transform of that original function, but then we have to subtract our initial condition. So that initial condition here is the same as saying for our variable in this problem is x, this would be x of 0. What is happening, or what is the position at time 0? Okay, now let's look at the second derivative because it's very similar. The second derivative says, oh, you need to do that same process again. So we get, instead of just an s times f of s, we get an s squared f of s, and then we subtract s times our initial condition minus our initial velocity, okay? So here, this is the same as s times x of 0, and this is the same as x dot of 0, okay? So notice we are specifically plugging in the time equals 0. These are initial conditions. These will simplify down into a scalar times s, or just a scalar, whereas this one stays as the function big F of s. Okay, so let's try that out on our own. So for our double derivative here, we should have s squared big X of s minus s x of 0 minus x dot of 0. That's all for this guy. I sometimes, it's kind of hard to tell the difference between a capital X and a lowercase x unless you make it really obvious, especially because the way that I've written it has kind of slowly gotten smaller, or no. So what you'll see a lot of people do is put little feet on the capital X, but I think it's such a big pain in the butt to do 4 different dashes that I save time by doing this. So that, I hope it doesn't bother you. That's my capital X. This is to make it really clear that it is different from my lowercase x's, which I try to make a little more scripty. Okay? All right, so that was our left-hand side. This is equal to stuff on our right-hand side. So the Laplace transform of the left-hand side, remember, it's a linear operator, so this means that we can do the Laplace transform of minus 4x dot. We can just care about that one. Minus or plus the Laplace transform of minus 3x plus Laplace transform of 9u. Linear operator lets us do that. So let's hone in on just this minus 4x dot. So x dot is a first derivative. So I'm gonna ignore our minus 4 for a second because it's gonna multiply everything that has to do with this x dot. And remember, we have a single derivative, so we multiply by an s, capital X of s, minus what? X of 0, very good. Our initial position, okay? A little simpler because it's a first derivative and not a second derivative. Plus, what happens with this guy? So we know that our negative 3 doesn't do a whole lot. It just comes out of the problem, right? What is the Laplace transform of little x, Shane? Big X, yeah, that's all we're gonna do. Don't overthink it too much. Whoa, that was really bad. All right, so this one just becomes big X of s. Big X of s plus Laplace transform of 9. What is the Laplace transform of our step function? I always forget. I'm going to go back and look. Step function, 1 over s. 1 over s. All right. That looks a little messy, so let's try to clean it up. We've got, let's see, s squared, big X. What was x of 0? I didn't tell you. Let's assume our initial conditions are x of 0 equals 1 and x dot of 0 equals 0. Copy. Paste. Okay, so minus s times x of 0, which is 1, so our s stays there, minus x dot of 0, which is 0, so that goes away. So minus 4s big X, x of 0 is 1, minus 3 big X, plus 9 over s. Yes, I do. Yes, you're right. Thank you. So that should be plus 4. I did the same thing when I was writing these notes. Thank you. Got it. Getting better.
It is the flimsy bag of M&Ms that doesn't help.
That might be the thing. Okay. So what are we aiming to do with a differential equation? We want to know what is the behavior of this system, right? So ideally, I would like to know what is x over time, given the fact that I forced it with this sudden 9 force at time equals 0, right? So what I would like to do is isolate big X of s, get it on one side of the equation, take the inverse Laplace transform of everything, and arrive at x of t. So let's do that. Let's see what that looks like. So I want to isolate big X. So let's do s squared. Actually, let's maybe rearrange a little bit differently. Let's do s squared plus 4s plus 3, everything that multiplies in x, minus s minus 4 equals 9 over s, okay? So a couple rearranging steps all in one. Let's try to get this s over on the other side. So we just need to multiply s times s squared plus 4s plus 3, big X, minus s squared minus 4s equals 9. Okay, now we can move these guys over. So we'll have s squared plus 4s plus 3, big X equals 9 plus s squared plus 4s. Now I can divide and I'll have x on its own. So I have, I'm going to just write this a little more pretty. So s squared plus 4s plus 9 over s squared plus 4s plus 3. Okay. Sweet, we got x isolated. Now I have a question. How the heck do I take an inverse Laplace transform of that? Ah, someone did their reading. Yep. Yes, we're going to do a process called partial fraction decomposition. So if you got to this point and you were like, oh gosh, I don't know what to do, let's have a potentially useful aside. Let's look at a different case. Let's say I have something that looks like this, where I have 1 over an s plus a times an s plus b. Okay, so we maybe factored the denominator a little bit. In order to look more like the tables of inverse Laplace transforms that I have, or Laplace transforms, I would rather have a sum of fractions where there's only one term on the bottom instead of 2 terms being multiplied. Okay, so I'd rather I be able to take something that looks like this and turn it into something that looks like this, because these things are on my table. right? I said, we're gonna look a lot at things that have like a number over s plus a. Okay, so the question is, how do we do this? Well, there is a process. I don't know who came up with it. I think it's beautiful and elegant and I love it, but I could never for the life of me have figured it out myself. So let's go through the song and dance together. So what I would like to see happen is let's maybe make this a little more concrete. Let's assume that we're dealing specifically with a equals 3 and b equals 1. So let's say we have 1 over s plus 1 s plus 3. I want that to look like some number over s plus a plus some number over s plus b, and I specifically chose a and b as 1 and 3. All right. So we say, I want to force this thing to happen. And if I'm going to force this thing to happen, I'll need to solve for what are a and b that cause this to be true. So let's start out by multiplying each of these terms separately by a special form of 1. Are we okay with that? Multiply a fraction by 1, still the same fraction, right? Okay. I'm going to take this s plus 3 over s plus 3. That's 1, right? It's a special form of 1. Looks a little gross, but it's 1. Times a over s plus 1. Now I'm going to do it the opposite way. I'm going to say s plus 1 over s plus 1 times b over s plus 3. The denominators look a little more correct, right? Now, on both the left and the right, I have an s plus 1 times an s plus 3 on the denominator. All right, let's simplify a little more. So on the denominator, I should get as plus 3a over s plus 3 s plus 1 plus bs plus b. It's not bs. It's true. S plus 1, s plus 3. Okay? We could simplify even further because these things add, right? Because the denominators are the same. So really we could even smush it all into one fraction. Okay? Let's compare these two things now. If these two things are in fact equal, the numerators have to equal and the denominators have to equal. The numerators, that looks a little hairy, but the denominators, those are good. So let's compare the numerators. And in fact, let's arrange these things as though they look like polynomials in terms of s's. So on the left-hand side, I have just a 1, but really this could be 0 times s squared plus 0 times s plus 1. That's still 1, right? Yeah? And on the right-hand side, I have a plus b s plus 3a plus b. Okay, it turns out I don't actually need to care about an s squared, even though it's multiplied by 1. Okay, if these two things are going to be equal, then my coefficient of s on the right has to equal my coefficient of s on the left. My constant on the right has to equal my constant on the left. Okay, that's two equations, and I have two unknowns, an a and a b. Two equations, two unknowns means I can solve for two unknowns. All right, so let's see what that looks like. I need everything multiplied by s to equal 0. So I have 0 equals a plus b. And I need my constants to sum up to 1. So 1 equals 3a plus b. Okay, I am running out of time more than I hoped, so I'm going to allow you to have faith in me that big A comes out to, I think, 1/2. And big B comes out to minus 1/2. Okay, which means that 1 over s plus 3, s plus 1, equals 1/2 over s plus 3 plus minus 1/2 over s plus 1. Okay, and this is something that we can take an inverse Laplace transform of. I can take an inverse of the left and I can take an inverse of the right. All right, so let's hop back to our actual problem here. We have, I'll remind you, our big X was equal to 9 plus s squared plus 4s over s times s squared plus 4s plus 3. Okay, on the bottom here, we can factor this a little further. What does it factor into? Positive 3, positive 1, absolutely. Who said that? I heard it, Shane. Getting better, heck yeah. I really should practice before class, but it's more fun to embarrass myself. Over s plus 3, s plus 1. Okay, this is a little bit more complicated. We don't have just 2 terms, we have 3 terms. How do you think that changes things? We have another term c, right? So it's 3 things added together. So we now have, what we want to turn this into is something that looks like this. Equals a over s plus b over s plus 3 plus c over s plus 1. Next step, what do I do?
Same process we just did,
Okay, which started with
multiplying by the denominators.
multiplying by special form of 1. Yes. Jerry, I'm not going to throw at you. Okay, but our special form of 1 has to be a little more complicated this time. Our special form of 1 has to have all the other terms. Okay, so here I'm going to say this is s plus 3, s plus 1 over s plus 3, s plus 1. It's still 1, looks ugly though, times a over s. Same thing here, we have an s times s plus 1 over s times s plus 1, b over s plus 3, plus s plus 3, s plus 3, c s plus 1. All right. Denominators look great. That's exactly what we have on the left-hand side. The numerators, we're going to have to chug through and do some algebra. So this first one, you can either use FOIL. I don't like FOIL. I don't know why. I multiply polynomials using boxes. This is the multiplication of these 2 things. This one is the multiplication of s and 3. This is s and 1, and this is 3 and 1. So that should come out to a times s squared plus, add these 2 things up, that's 4s plus 3. I'm not going to write out the denominators because they stay the same. And then the rest is just moving that s into the parentheses. So it's plus b times s squared plus s plus c times s squared plus 3. Yep. Wait, where?
For C.
3s, yes. And I did it right here because it was 1. Got it. Okay, yep. Okay, so these are all grouped by, this is what multiplies A, this is what multiplies B, this is what multiplies C, but we need to regroup it so that this is what multiplies s squared, this is what multiplies s, this is our constant, so that we can compare it to what's on the left. So I have s squared plus 4s plus 9 over here is equal to, let's get everything that multiplies an s squared plus everything that multiplies, I'm so close, s and a constant. So we should have a plus b plus c, if I did that right. S's would be 4a plus b plus 3c, and constant should be 3a, and that's it. Is that right? Okay, so now our three sets of equations are 1 equals a plus b plus c, 4 equals 4a plus b plus 3c, and our last equation is 9 equals 3a. Okay, so I can immediately see that a is equal to 3. I can plug that back in anywhere that I want. Let's do it maybe here. So I have maybe 1 minus 3 is minus 2 equals b plus c. Let's solve for b. We'll say b is equal to minus 2 minus c. Take that, plug it in over here. Get 4 equals 12 plus minus 2 minus c plus 3c. I can solve for c now. C ends up being minus 3. Okay, if I plug that back in here, I get b equals to 1. Okay, so my solution here is a equals 3, b equals 1, c equals minus 3. Okay, I ran out of time to do the inverse Laplace transform. So we will pick up here Tuesday, finish off this problem together, and then we'll move on to everything else that we have. So my last bit of information for you today are just some reminders. Please do read Chapter 2, Section 10 and 11, as well as Chapter 3, 1 through 7. Your group project selection, I've heard some people have already done it. Well done, thank you. Those selections are due next class. There is an assignment on Canvas. Please only one group member submit the assignment with all the group names. And then our next topics are going to be nonlinearities, linearization, and state space. Okay, but we will finish this problem together, so don't worry too much. Okay, thank you all so much. Yes.